Okay, now today we're going to start talking about symmetry and the golden ratio. Patterns in geometry occur in nature, and people have been noticing these patterns since the dawn of humanity. For example, they've been using the golden ratio in Greek architecture for back over 1,000 years. Okay, um, in this chapter, topics in geometry will be examined. These topics include transformation and symmetry of geometric shapes, similar figures, gnomons, Fibonacci numbers, and the golden ratio. So in this section, we're going to start by talking about transformations using rigid motions. Okay, we're going to learn about isometry, or what we call rigid motions. In isometry, an isometry is a transformation that preserves the distances between the vertices of a shape. Okay, a rigid motion does not affect the overall shape of an object, but moves an object from a starting location to an ending location. The resultant figure is congruent to the original figure. Okay, so here are some definitions that you're going to want to know. So the first one is rigid motion. A rigid motion is a transformation that moves an object from one location to another while keeping the size and shape of the object unchanged. Okay, two figures are called congruent if and only if there exists a rigid motion that sets up a correspondence of one figure as the image of the other. So side lengths remain the same and interior angles remain the same. Identity motion. The identity motion is a rigid motion that moves an object from its starting location to exactly the same location. So it doesn't seem to move. So it's if the object has not moved at all. Okay. Um, let's see. Given a rigid motion T, the inverse motion is a rigid motion T inverse such that T followed by T inverse results in the identity motion. That is, the inverse motion moves the object back to its starting location. So T will be a rigid motion, let's say is a rigid motion that moves the object to an ending location that is different from the starting location. And let's say the inverse motion, T inverse, moves it back to where it started. Okay. Now, let's move. Here we go. Now, there are four kinds of rigid motions that we're going to talk about. One is a translation, rotations, reflections, and glide reflections. Okay. When describing a rigid motion, we will use points like P and Q located on the geometric shape and identify their new location on the moved geometric shape of P prime and Q prime. Okay. We will start with the rigid motion called a translation. When translating an object, we move the object in a specific direction for a specific length. Okay. The direction length of the motion is usually described by a directed line segment, like a vector, okay, which we will call a vector. Okay. So again, translation, think of an algebra when we do a translation of a graph, right? Same idea. Same idea. Okay, now here's a definition. A translation of an object moves the object along a directed line segment called a vector, which we will use denoted by lowercase letters with an arrow above it, for a specific distance and in a specific direction. The motion is completely determined by 2 points P and P prime, where P is on the original object and P prime is on the translated object. Okay, so here's an example of how we would show a translation of a triangle. So the original triangle is in blue, and then the ending location for the triangle is in red. So there's the P and P prime. Okay. The translation of the blue triangle with point P was moved along the vector V to the location of the red triangle with point P prime. Also note that the other vertices of the blue triangle also moved along the vector V to correspond to vertices on the red triangle. In ordinary language, a translation is an object is a slide from one position to another. Okay, you are given a geometric figure and an arrow which represents the vector. The vector gives you the direction and distance which you slide the figure. Okay, so let's look at this example here. Okay, so here, notice that we're given a vector V, right? So the vector V gives you the distance and the direction that you're going to slide the triangle here. So the blue triangle, BAC. Okay, so we're going to move it how many units? We're going to basically move it 3 units up. Okay, so that means B is going to move here. Okay, A is going to move where B was, and C is going to move here. Oh, hold on a second. Oh, hold on. Oh, I didn't move it right. Here. Sorry. A is going to move here. That's wrong. Hold on. Let me... Okay. So B, or A is going to move here. I put it in the wrong spot. And then C is going to move here. Okay, that looks right. Okay. And so now, the new position is going to look like that. Okay, and let's see what we did. So there it is. So notice how here we have B prime. I didn't put the primes, but we have B prime and then A prime and then C prime. And I didn't put the directional arrows as well. Probably should have put that as that too. But you get the idea. Okay, so the vector V extends vertically for 3 units. So we start by moving each vertex of the triangle vertically for 3 units. Then we draw the edges connecting the vertices to get the image shown as a yellow triangle, which is what I did in above, right? Note that when we moved the triangle, all of the points on the triangle moved, not just the vertices, but also all the points along the edges. That is, there are no fixed points. Moreover, if we wanted to move the triangle back to the original location, we would just have to translate it 3 units in the opposite direction, and that is, we're going to go 3 units straight down. So more generally, we have these properties of translations, or of a translation. So the properties of a translation is 1, a translation is completely determined by 2 points, P and P prime. 2, a translation has no fixed points. And 3, the inverse motion is a translation along the vector negative V, where negative V has the same length of vector V, but points in the opposite direction. Okay? Okay, so let's look at the next example. Okay, so now look at this. So we've got this P, right? Point P. So here we got point P, and we've got this vector. Okay, and the vector is telling us the length and the direction. So that means this point here, right, is going to move to here. And this point here is going to move there. And then this point here moves there. This point here is going to move here. So I'm just taking all the corners, all the points along the vertices, right? And I'm moving them here the same way. And then finally, we have that. And so now I'm going to connect the dots. Carefully. Okay, now, again, my drawing's not the best, but you get the idea. So now what I'm going to do is I'm going to connect, right? Let me use a different color. So I have this. Oops. Right, something like that, right? Well, that last line we don't need. I don't think. Okay, so there's your translation. Okay. And see, that's what they did. Of course, they shaded it in, right? I'm not going to take the time to shade it in. So the vector V moves horizontally, what? So here's another way of looking at it. It moves every point, every vertex, it moves up horizontally 2 units and to the right 3 units. Okay? So we start by moving each vertex 3 units to the right and 2 units up. And then we fill in the edges. And then the red figure is the position of the L-shaped figure after the translation has been performed. So the next type of transformation that we're going to talk about, which is a rigid motion, will be a rotation. Now, a rotation, by definition, of an object moves the object around a single point called the rotocenter, R, and it's rotated by a specified angle, theta, either clockwise or counterclockwise. Note, the rotocenter can be outside the object, inside the object, or on the object. In the 2 figures below, the blue triangle below has been by a specified angle about a point R. So if we look here, so let's look at this. Okay, if we look at figure 2, triangle rotated 90 degrees around rotocenter R outside the triangle. So here's the rotocenter, right? Okay, and so you're going 90 degrees, so the blue triangle rotates 90 degrees clockwise. Okay? Whereas if you look at figure 3, it's been rotated 180 degrees about the rotocenter R. So here's the rotocenter, which is in the center, in this case, inside the figure. Okay? And so this point here, right? This point here has been rotated 180 degrees to here. And likewise for every other point, right? So this point here rotates to this point here. Or excuse me, oops, sorry. I did the wrong point. This point. So this point here rotates to here, and this point here rotates to here. Now, note that when we perform a rotation, the rotocenter remains fixed, and it is the only fixed point for this transformation. Moreover, if we rotate by 360 degrees, the figure will come back to its starting position, so it'll look like it didn't even move. So this means that a rotation of 360 degrees is the identity motion. Another key property of rotations is that they are additive. Okay, that is, if we do a rotation by alpha degrees, followed by another rotation by beta degrees, then we will have the same outcome as if we did a single rotation by the sum of the two angles alpha and beta. So we have alpha plus beta degrees. In particular, if we rotate by alpha degrees followed by a rotation by 360 minus alpha degrees, the result will be a rotation of 360 degrees, which is the identity. Okay, so we can use subtraction as well. Thus, the inverse of a rotation by alpha degrees is going to be a rotation of the 360 minus alpha, which gives us the remaining amount of rotation needed to go back to where we originally started. Now, finally, every rotation can be described by an angle between 0 and 360 degrees. For example, if we did a rotation of 405 degrees, this would be the same as rotating by 360 degrees followed by a rotation of 45 degrees. The 360 degrees is an identity motion, right? And so we could describe the same rotation by just saying 45 degrees or using a rotation of 45 degrees. Okay, so now we're going to summarize all of these properties below. And so here are the properties of rotation. 1, a rotation is completely determined by two pairs of points, P and P prime, and Q and Q prime. 2, a rotation has a one fixed point, the rotocenter R. 3, the identity motion is a 360 degree rotation. 4, the inverse of a clockwise rotation by alpha degrees is a clockwise rotation by 360 minus alpha degrees. Alternately, the inverse of a clockwise rotation by alpha degrees is also a counterclockwise rotation by alpha degrees. Okay, again, as long as you end up going back to where you originally started. Okay, so let's look at another example here. Okay, so look at this. So again, we're given this rotation. Okay, so now what is this be telling us? So here's Q, right? Q is this point here. So I'm gonna, all the vertices, so there's that point. Okay. So I'm going to mark all the vertices. Okay, so now this is a 90-degree angle, right? So you're going from Q, so to Q prime. Okay, so Q to Q prime is rotating 90 degrees, so this is going to go here. Okay, um, and then what's going to happen? What's happening? Effectively, what's happening? Every point is going down one and to the right three. Is essentially what's going on. So I'm going to move all the points 90 degrees as such. Okay, and I'm going to estimate here because some of these are not on a grid nicely. Again, my drawing isn't perfect. Okay. And of course, obviously the illustration will be better, but if we let me scroll down and show you. So there we go. Oh, I screwed up. I was thinking of a rigid motion, a translation. Um, okay, so let's back up here. So in this case here, it's a 90-degree rotation, which means um, this is going to rotate. So this point Q is going to rotate to Q prime, which is right here. This is going to rotate 90 degrees to here. This point is going to rotate 90 degrees, which is going to be right about here. And this point, let's see, this point is going to rotate right about here. And then the point here is going to rotate. I'm just going to mark the points here approximately. Okay, and then we got this point. Okay, so what's going to happen is then if I connect the dots, it'll look something like this. Okay, I'm not going to shade it in, but if you rotate up, this is what we get. Okay, so the point Q, bottom left vertex figure, okay, which is right here, is rotating 90 degrees. Note that Q is 1 unit left and 2 units down up from R. Okay. After the rotation, the image Q prime is 1 unit up and 2 units right from R. Okay, so now rotate each of the other vertices 90 degrees clockwise as well, and then fill in the edges. The red L-shaped figure will be the result. In other words, the red L shape is the image of the original blue figure when rotated 90 degrees clockwise. Okay. Okay, so let's look at another example. Notice this here. Look at a 45-degree angle. Again, we're rotating at 45 degrees clockwise around the rotocenter as shown. And so notice that every point moves 45 degrees. So this point moves to here. And then this point moves 45 degrees, right, to about here. And here, and so on. Okay, so it's a 45-degree rotation. Okay. Now, what about a 180-degree rotation of an L shape? Okay, this is easier, right? Some of these are not as easy, like doing a 45-degree rotation, not as easy as doing 180 or 90-degree rotation. Okay, because in a 180-degree rotation, it's easy to find out where the points all go, right? Okay. So in 180 degrees, right, this point is R, so it's actually on the figure. So that's going to stay put. That's not moving. But this one's going to move 180 degrees, and it's going to go 3 units. Instead of 3 units to the left, it's going to end up 3 units to the right. And in this one here is instead going to be over here, it's going to be directly what? Instead of 3 units to the left and 2 units up, it's going to be 3 units to the right and 2 units down, right? And then this one's instead of going 2 units directly up, or excuse me, 1 unit directly up, it's going to be 1 unit directly down. Okay, and so now, oh, and what about this one? This one is this vertex here is exactly what? 2 units to the left, 1 unit up. So now it's going to do 2 units to the right, 1 unit down, right? And so now all I have to do is connect like so, okay, which is what we did over here. And of course, label all the vertices with the A prime and B prime and at least the 2 vertices, right? Because you only need 2, okay, because it's a rigid motion. Okay, the next type of transformation that we're going to talk about is called a reflection. A reflection is a mirror image of an object, or can be thought of as flipping an object over. So here's the definition. Let L be a line in the plane. Then the reflection across L is a rigid motion that sends any point P to a unique point P prime. Such L is the perpendicular bisector of P prime. Okay, so that's the line segment. Okay, perpendicular bisector of P prime. The line L is called either the line of reflection or the axis of reflection. Okay, so let's look at this and put some teeth to it. So here we go. So if we have a line of reflection, right? So reflection across line L. So here's line L. Okay, if we were to reflect P to P prime, right? If we do that, then the line segment that connects P and P prime would be congruent on both sides. So yes, so L is the perpendicular bisector. Perpendicular because it forms an automatic right angle, and we can see that let's call this O, we can see that line segment OP is congruent to line segment OP prime. Okay? So in plain English, we might describe a reflection as a mirror image across a line L. From the definition, we see that any point on the axis L is a fixed point for this rigid motion. Moreover, if we know the line L, then we can determine the image of any point. Okay? Conversely, if we know the image P prime of a single point P that is not on the line, we can determine the line by constructing the perpendicular bisector of PP prime. Finally, if we do the reflection twice in succession, we see that every point is back where it started. So that is, reflection across a line L is its own inverse. So if we do a reflection across line L twice, we get back to where we originally started. All right. So here are the properties of a reflection. 1, a reflection is completely determined by a singular pair of points, P and P prime. 2, a reflection is completely determined by its axis L. And 3, a reflection has infinitely many fixed points. Every point on the line of reflection L remains fixed by the motion. Okay? In other words, there's an infinite number of points that are on the line L of the line of reflection, the axis of reflection, that that goes, if it goes through the shape. Okay, and then 4, a reflection is its own inverse. That is, performing the reflection twice in succession will return the object to its starting location. Okay, so let's look at an example. Okay, so here we go. So in this example, we have the blue object, right? And L, so here's L. So we're going to reflect all of these points to the other side. So the reflection across L means that C is going to go to C prime, which is right here. And then B is going to be reflected on the other side. So it's going to go 3 units to the right to 3 units to the left of the line. And then A will go also from 3 units to the right to 3 units to the left of the line. Okay, so again, this is going to be C prime. And this is going to be B prime. And this is going to be A prime. And then, of course, we have this. Right, and so we get something that looks like this. Right? And that's what we have down here. And notice we have the directional lines, right? Okay. The reflection places each vertex along a line perpendicular to L and equidistant from L. After plotting the images A prime, B prime, and C prime, we fill in the edges to get the image of the object, which is in red on the left. Here's another Example. So now in this case here, we've got the axis, right? The L, the axis of reflection, is going through part of the figure. Okay. So again, we're just going to rotate it about this line, or reflect it about this line, where all the points along the line L are going to stay fixed. So again, this B is going to end up flipping over to here. So this is B prime. Okay. A is going to flip across to here. And then C is going to flip across to here. To C prime. And so what do we get? We get something that looks like this. Right? Something that looks like that. Okay, as we can see below. So this one is slightly different as the line of reflection passes through the figure. However, the strategy is the same. We reflect vertices A, B, and C and fill in the edges between the images A prime, B prime, and C prime. The red L-shape shown below is the result after the reflection. Since the line of reflection is vertical, the original position of each vertex on the horizontal line will with the reflected position of each vertex. Okay, it's on a horizontal line with the reflected position of each vertex. This line that connects the original and reflected positions of the vertex is perpendicular to L and the original, okay, and reflected positions of each vertex are equidistant from line L. Okay, so the properties of reflection are preserved. Okay, so now let's look at this one here, this example. Now notice that this is not a reflection horizontal or vertical. Okay, so again, we want to do things, map these out carefully, right? Because this is a reflection across line L, and line L is at a 45-degree angle. Okay, so first we identify and label the vertices of the figure. From each vertex, draw a line segment perpendicular to L and make sure that the midpoint lies on L, right? So what we're doing is we labeled A, B, C, and D, and then we're basically drawing a line segment that's perpendicular and equidistant from line L. So then we plot the points here, 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 and here. Okay? And so now those are going to be the prime points, right? And so notice that's what we do up here. So notice how now look at this. This looks like a mirror image, right? The red is a mirror image of the blue image. Okay? And so we get the same thing when we connect the dots. Okay? The final transformation, which is also a rigid motion that we will study, is a glide reflection, which is simply a combination of two of the other rigid motions. So a glide reflection is a combination of a reflection and a translation. Okay? So here we go with the smiley face, right? So we're going to find the image of the reflection shown by doing a glide reflection. So notice how we have a vector and the line of reflection or axis of reflection. So notice here. So what we're going to do is we're going to slide the smiley face 2 units to the right. Okay, so we're going to go 2 units to the right, and we're going to have our smiley face inside the 4 squares. Okay, so we've got our smiley face is going to slide this way, right? And then we're going to do the reflection, which is going to go down here, right? Reflected across in these 4 squares, right? So it's going to, and the eyes are going to be down here, like so. Okay, so this is a 2-step process. First, slide the smiley face 2 units to the right along the vector V, then reflect the smiley face across line L. The final result is the green upside down smiley face. Okay, the final result, right, is that. Okay, so some of these, it does require mental gymnastics, right? You've got to be able to visualize what's going on with doing multiple rigid motions. Okay, so here are the properties of a glide reflection. So 1, a glide reflection is completely determined by a single point, or excuse me, a single pair of points, P and P prime. 2, every point on the line of reflection L is a fixed point. 3, the inverse motion is the reverse glide reflection that was given. That is the combination of translation by negative V, the vector negative V, followed by the reflection across line L. Okay, so that would be the inverse motion. Okay, so now if we look at this example here, we've got this triangle, and we've got this vector V, and we've got this axis of reflection L. Okay, so we first are going to do the translation. So we're going to move the vertices. So we get, let's say here, we've got these vertices here. They're labeled below, but I'm going to just label the points here, right? So this, we're going to move the points at a 45-degree angle according to the vector V to its new location. Oops, I missed that one. Okay, so it's going to move here. Oops, that's too bad. I'm going to do a little better. There we go. Okay, now that's only part of it. So now what we're going to do is we're going to reflect it across here. So this is going to go, so this point is going to reflect across to here. So one vertex is going to go here. The other vertex is going to go here. And the other vertex is going to go here. And so now if I connect these dots, I get that. Okay, so I get the same result right down here. So notice how they used the stars, right? Asterisks. So to represent the two-step transformation, which is totally fine to do that. But realize that the ending location, the ending figure, is the green triangle. Okay? So again, it's a two-step procedure. First, slide the triangle along the vector, and then reflect it across line L. Now, could we do the reflection first and then slide? Sure, we could do that. We would have got the same result. Okay, so now let's look at this one. Okay, let's look at this example here. So again, we've got our vector, right? So it means this translation is going to move every point up to and to the right 5, right? So that's what we're going to do. So we're going to go up to over 5. And so I'm going to plot the points. Okay, so we get this. And I'm trying not to look at the figure below. So trust me, I'm just doing this. So it looks like that. Now what I'm going to do is I'm going to reflect all the points across the line. So this, so one point's get on the lines. Well, it's almost on the line, but we're gonna flip this one. So I'm gonna put a point right here, and this one's gonna go approximately. Let's see here. Here. Where's that going? That's gonna go. So this is gonna go approximately right here, and this is gonna go right about here. So I'm kind of guessing. This is a little more difficult with this reflection, but you get the idea, right? So we moved it down here, and then this is going to be here. So this reflection, right? So these 2 points here, and then this point flips to here. This point flips to here. This point flips to here, and so on. Okay, and that's how we do it. So again, like the previous examples, there are 2 steps. First, slide the L-shaped along the vector V, which gives the red shape on the left, and then we're going to reflect the L-shaped red shape across L to get the open green shape on the right as our final figure. Oops. Something happened. Uh-oh. Oh boy. Hold on a second here. Something's not right. Okay, we'll just end there. I'll come back.